Now let's talk about Lagrange interpolation method. Lagrange interpolation method probably is the most interesting for me, at least, among the interpolation methods, because it's very famous among those who work with finite element analysis. Although in many cases derivation of the Lagrange polynomials can appear not straightforward, I don't think so myself, and I see them as derivable as easy as 1, 2, 3, as we may see together here. In Lagrange method, you need to pass the polynomial just like any other polynomial in interpolation through the points given. So you're going to use this time different looking polynomials. These polynomials are ones that are equal to 0, are going to be equal to 0 at all points and equal to 1 at the point of interest. Well, it's much simpler than it sounds, actually. Let's start with our easiest polynomial, which is a line joining 2 points, x1, y1, x2, y2. Let's now propose our solution or our interpolation function in the form of a constant times x minus x1 plus another constant times x minus x2. You can notice here that x minus x1 is a form of a linear relation. When you plug in x equals x1, this will become 0. While on the other term, when you plug x equals x2, you will get also a 0 here. So at both ends, one of the terms of the proposed polynomial is going to be equal to 0. Let's use our data x1, y1, and x2, y2 to find what are the values of c1 and c2 that will satisfy this polynomial. First, let's plug in x equals x1, y equals y1, and right away you get c2 equals y1 over x1 minus x2. Using the other point, y2 and x2, again, you lose this term and you solve for c1 right away to get c1 equals y2 over x2 minus x1. Plug those two constants back into our original equation to get something that looks like this. What's noticeable here is the first term, again, is a line that's equal to 0 at x2 and equals to 1 at x1, multiplied by the value of the function at that point, x1. The same, you get here, it's 0 at x1, this is the second line, the second polynomial, and equals to 1 at x2, and multiplied here by a kind of a weight, a coefficient, a weighing constant, equals y2, to make it equal to y2 at x2. This actually is quite an interesting way of presenting polynomials, because this is what most of the finite element models use. If we approach this problem, at least if you're interested in finite element analysis, if you approach it through this way, the Lagrange polynomials way, you kind of get it very systematically. You don't need to look into books and formula sheets to get what polynomials you're going to use for that element or this element and so on. Let's explore it a little bit further together. First, of course, you need to rearrange the terms of the polynomial we obtained here, these terms, and see whether you'll get the same results that you got for general polynomials, which was in the form a0 plus a1x, and see if this is what you get or not. of course, you know that you will get the same polynomial. Okay, now let's go for 3 points. Now we want to use a parabola to interpolate the function, to create a function that passes by those 3 points. So here is our parabola. We need 3 coefficients, so 3 terms are going to be used, each of which is a second order term. The first term is x minus x1 times x minus x2. The second will be x minus x2 times x minus x3. And of course, the third will be x minus x3 times x minus x1. You follow the same procedure. Plug in x1, y1 to get C2. And similarly, you get C1 and C3. Finally, just put it into the relation, and let's wait here for a few seconds to really read what we have. 3 terms, each multiplied by a coefficient. Each of the 3 terms is a product of 2 linear terms. So what you get here is second order term, and another second order term. If you try to evaluate those second order terms at, say, for example, the first one, if you plug in x2 or x3, x2 will get this to 0, x3 will get this to 0. So actually, the whole term is equal to 0 at x2 and x3. On the other hand, if you plug in x1, you will get x1 minus x2 over x1 minus x2, and x1 minus x3 over x1 minus x3, so you get 1 times 1. Again, the same as we saw in the linear example, but a little bit longer. These parabolas, if you if you draw each of them, you'll see that if we selected, of course, x2 to be 1/2 and x1 to be 1, x1 to be 0, you'll get parabolas that look like this. Here is the first one, 1 at 0, 0 at 0.5, and 0 at 1. The second one, 0 at 0, 1 at 0.5, and 0 at 1. The third one is 0 at 0, 0 at 0.5, and 1 at 1. This is going to be repeated all the way. Every time you use Lagrange polynomials, this is what you're going to get. As a matter of fact, you don't need to work through C1, C2, C3 anymore. You can see right away that the outcome will be polynomials that are multiplied by y1, y2, y3. So you can just write down y1, y2, y3. Then start taking all the combinations of x's, x1 minus the other x's, and use them. Then for y2, use x2 with the other x's. For y3, use x3 with the other x's, and so on. Now let's go back to our famous cubic polynomial. Here you have the 4 points. We want to interpolate a third order polynomial through those 4 points without any calculations. Actually, you write down the relations. Here you are, 3 brackets, each of a linear term multiplied together. Then each of the 4 polynomials are multiplied by y1, y2, y3, y4 respectively. Plug in the numbers. There you are. Simplify it. You're going to get these relations. Now you can use this right away, expand it, rearrange it, or whatever, but it's really beneficial in many cases to keep your polynomial in terms of the values of y at the different points, and that's the main thing that the finite element model actually looks for in any polynomial. Finally, plug in all the numbers, rearrange, and do the rest of the homework yourself by proving that you're going to get the same polynomial you get from Newton method and the one that you got from the general polynomial approach.